Hello, my name is Eric Hoffander, and I'm a graduate student in the Electrical and Computer Engineering program of CSU. For the final project in ECE 561, I designed and built a self-powered wood stove controller to help heat my home. As I cut wood from my own property, the heat they provide is carbon neutral. However, heating is a lot of work. To properly heat the house, I need someone to check on the fire about every 10 minutes to make sure it stays above the creosote generating temperature, where the unburdened wood will congeal inside the pipe, and below the temperature where I lose the majority of the heat right out the exhaust pipe. Ideally, I want to replace the whole thing with a machine just to do it for me and do a far better job. Starting the project, there was a few critical challenges to overcome. The first one is safety. I can't drill holes or screw things into the unit without breaking the fire code. And as I use the stove during power outages, I don't want to rely on grid power. As you see here, I already use thermally powered fans on top of the stove to move the air. Can I use the same principle to drive the control system? There's a huge thermal gradient between the air and the stovetop. Can I use that to power the full control system, monitor the stove, drive a UI, all while never plugging my stove into the wall or spending way too much money? The stove runs fairly infrequently, so I need it to run for a long period of time without any external power. The first step in any controls project is to model the system and build the control system in software. Thankfully, the EPA makes manufacturers publish all the specifications for wood stove, including the thermal mass, the power output, and the airflow. I modeled the full system in Simulink, along with some very basic assumptions. This allows me to solve for the PID coefficients without measuring the transfer function physically, which would have been very difficult given the long fundamental time of the system. The main challenge here is that the wood stove is going to have a non-linear throttle response as the wood logs burn. I also cannot add wood slowly. Opening the door to add a log caused a huge thermal shock to the system that I was unable to model. As my goal here is a passive device, one that harvests its own energy, all the hardware was selected to minimize the current draw while in idle. The ESP32 SoC I chose is a unique dual-core device, with one high-performance CPU with a selectable clock cycle, and one real-time clock processor with the ability to run on nanoamps of current. While in deep sleep, the RTC can capture hardware interrupts and generate software interrupts timers for the main processor. This will be critical for writing the firmware. High-temperature K-type thermocouples were used for the firebox temperature. As they are rated to 1000 degrees C, this provides a good safety margin over my target of 450 degrees. Two Seebeck generators will provide electrical power to a DC-DC buck boost converter. This will generate a steady 5 volts DC to the board when they're above 200 degrees C. This is used to charge a lithium-ion 18650 battery, which provides both a high current draw to the actuator and will power the system when the stove is cool. The UI is provided by a black and white watch OLED screen. The power is in proportion to the number of illuminated pixels, so even when active, it only draws 4 milliamps. My main problem is the H-bridge in the linear actuator. Without designing a custom actuator, I'd use an off-the-shelf part with 10,000 times the force required. Limiting its active time will be critical to stay within my power budget. To keep from modifying the stove, I attached the actuator to the base with discarded hard drive magnets. The digital circuit layout was very simple. All chip communication was implemented via the serial peripheral interface. This greatly simplified the coding as well. Requiring only 2 I/O lines per chip meant that the circuit was very easy to wire, but limited the amount of data I could display on the screen. As I only planned to update the screen once per time step, this really wasn't an issue. The thermocouple ADCs and ambient sensors all shared SPI lines as well. As my sensors required much more current than the CPU, I used MOSFETs to cut the power to the screen, sensor ADCs, and H-bridge while idle. If I had not done so, they would consume over 1,000 times more energy than the RTC. Coding this project in the Arduino IDE, with its lack of control over the compiler and the linker, was out of the question. To get the fine control over the hardware and the real-time scheduler, I used the direct ESP IDF from the SoC manufacturer. This allowed me to disable in hardware the Bluetooth and the Wi-Fi chips that came standard. This reduced the power consumption from 204 milliamps to 20 milliamps while active. The main state machine is built around increasing levels of power consumption. The goal was to maximize the use of deep sleep when we cannot harvest power from the stove. On reset, or deep wake, we jump to the main function. Here we look at why we woke up, an interrupt, polling, or a power on reset. We then enter the sensor state, where we power up the external ADCs and we wait for them to settle. Once we've uncovered that the temperature is greater than 40 degrees centigrade, we enter the control loop. Here we have 3 microtasks, each with a single task. The PID loop controls the main thermal control system. The UI task runs the buttons, the knob, and the screen. The actuator task runs the linear control system and runs the power on-off signals to the MOSFETs. So the first experimental runs were not very successful. Each time I would load wood, the system would go unstable. The system proved to be underdamped and had serious thermal swings. This caused the linear actuator to be in constant motion, draining energy from the system. It was failing to stay under 5 watts, so my system was constantly losing power, even with the stove at full temperature. With more days of testing and slowing the system down by a factor of 60, I was able to get the system under control. The proportional controller is now much less aggressive, and I allow the system to be overdamped at startup. During April, we had a 48-hour power outage in Estes Park, so this allowed me to run the system all day, tuning and updating the controller. Once I was happy, I let the system have full control over 5 hours without touching it. During this time, the average temperature error was less than 10 degrees inside the firebox. This is an order of magnitude better than I could do even standing directly in front of the firebox. The wood reloads still cause a large nonlinearity in the system, which the control system doesn't handle perfectly. If I were to extend the project, I would add detection code for rapid temperature loss, like the door opening, and use a modified controller during those time periods. On this screen, you'll see 3 different charts. So on the bottom left, you'll see the final 5-hour run with 2 times where I had to reload wood. On top right is the actual output of the thermal controller. So there's 3 different signals here. There's the proportional, the integral, and the derivative. They sum together to give you the control input to the system. And on the bottom, you see the linear actuator controller. This takes the input from the thermal controller and then directs the linear actuator to go to that position. While the sensors and actuators are powered on, the CPU power is a rounding error. The H-bridge I chose has a terrible idle power of 344 milliwatts when not driving the system. While driving the actuator, we spike above our generated power. With the reduced control system loop, the actuator is moving less than 1% of the time. Idle power use is so low that a fully charged 18650 could last me an entire season idle. The charge leakage dominates over the power usage of the system. The boost buck converter performed poorly and required higher temperatures than I had modeled. I could not generate power until the firebox is over 300 degrees C. I believe this is due to my cheap heat sinks. To extend the project, I would completely redo the power system to use a standoff and much better heat sinks. In the thermal view here, you see the 2 series-wired CBEC devices. They do not generate power based on temperature, but on the temperature delta. I should have used off-the-shelf wood stove heat sinks here. In the end, the largest power usage while idle was the status LED on the development board. There was no way in software to disable it, so I had to cut traces, or it would have consumed 20 times more energy than the entire idle budget. Overall, I had a lot of fun with this project. It was interesting trying to optimize a system for power rather than performance. It's incredible how little power a processor can use. Programming the interrupts for the RTC, updating the linker map for RTC versus DRAM memory was a new learning experience. I hope to improve the system next winter. With a printed circuit board assembly, an optimized C-back, and I want to experiment with solid-state actuators or make a friction DC motor mount. With less energy needed for the actuator, I could easily enable the Wi-Fi while the system is online, giving way to remotely control the system. If you're interested, I've released the full source code, the schematics, as well as writing up a paper on the system. Thanks everyone for watching.